So again, welcome to the first in our new series of Climate Ready Landscape Academy classes. And tonight is all about how much water does a garden need? This is the way that we are going to conduct the workshop. It's broken into 6 different topics. We're going to start talking about how much water plants need so that you can really understand what the mechanism is for watering plants. Like, how does it happen? The second thing is, what are the elements of an irrigation system? And then what could go wrong with that system? We're going to help you to track down leaks so that you save water just by fixing those. We're going to talk about converting from spray irrigation to drip irrigation. And then we'll spend a little time talking about how you can water your landscape more efficiently. It's really important for us to understand that the irrigation system, the outdoor water use, is what most households use water on. 29%, almost 30% of the water coming into a residence is actually going back out into the landscape and being used out there. And the irrigation system is by far the greatest water use in the outdoors. So this is why we're going to spend some time on this and try to get as efficient as possible. It's important, though, for us to really understand that we are not advocating getting rid of water in the landscapes. Now, you may hear us talk about how to reduce irrigation, how to eliminate irrigation, but it's important for us to remember that plants are actively cycling water. They are not just water users, they are actually water makers. And this is an interesting way to start to think about plants, to understand that this is how landscapes work. It's a cycle of water from soil into the atmosphere and back down again, and plants are in charge of that. And if we stop putting water into landscapes, either in the form of rainwater or in the form of irrigation, we are going to find ourselves aridifying our landscapes and aridifying our communities. And aridification is essentially desertification. It is the creation of a man-made desert. So we need to have landscapes, they need to have water, and we need to be as efficient as possible in helping them to have that water to thrive. And the way that we help landscapes become as climate ready as possible is by applying the watershed approach to landscaping. This is a set of principles, just 4 simple principles that we are going to use on every single landscape. And we are going to look at this landscape through a lens that it's a mini watershed. And we are going to concentrate on ways to capture water from the high point of the watershed, which is usually the roof, and hold it on the property and keep it from running off the low point of the watershed, which is usually, a driveway or something like that. And we have a lot of strategies for holding this water on the property and even supplementing that water as efficiently as possible. The principles are: we're going to capture rainwater and use it as a resource. Super important that we redirect the water from our roofs, from hard surfaces, and we keep it on, on the landscape and in the soil. We are going to build healthy living soil. We do that through several different strategies. The one you hear the most about is called sheet composting or sheet mulching, but really the very act of planting a diversity of plants in the landscape is a way of building that healthy living soil. Healthy soil creates a sponge, and that holds on to all that rainwater that we're redirecting into the landscape. We're going to select local and climate appropriate plants. For most of us, that means these are native plants or plants that are really adapted to our particular place. They are really the best and the most climate ready of any plant material. But there are plants from other areas that work, just as well in our landscapes. We just need to know how they fit into the ecosystem. And then finally, the fourth principle is if we are going to use supplemental irrigation, it's going to be highly efficient. And we're going to make sure that every drop that comes out of that irrigation system is staying on the landscape for the benefit of the plants. So the first thing that we are going to delve into is how much water plants really need. And the key is that, look, this is the water planet, right? So everything on the surface of this planet requires water, and all plants need some amount of water to thrive. Now, their favorite source of water is rainfall. But in the absence of rainfall, irrigation is meant to supplement rainfall. And it's important for us to remember that. It's not the only source of water, it's the second source of water for plants. The reason that we actually irrigate is to maintain a balance of oxygen and water in the soil profile. Plants need oxygen and they need the water. And we want to keep this balance in the soil so that the plants can grow what we call optimally. And that means that they're thriving, they're not struggling. You can stress them a little bit, but they're not actually struggling for water. So the important thing is, how do we figure out and maintain this balance and not allow it to become too saturated where the whole soil profile is just filled with water and there's no oxygen there. And so the plants actually suffocate in that environment. And the microbial activity that is alive in the soil are pathogens. And so we get lots of diseases when we have an oversaturated landscape. That's not what we want. And at the same time, we don't want to have a landscape where there's so much oxygen and there's so little water in that landscape that the plants cannot actually access the water. I think it's important to remember that even when soil feels absolutely dry to the human touch, there's still microscopic water films in the soil. And those films are coating every little particle of soil. But the challenge is that even though there is this little bit of water there, the plants cannot access it on their own. So we really want to make sure that we are neither, too wet nor too dry. We want to try to find that just right place where there is oxygen there, there's water, and the plant can actually extract the water as it needs it. And perhaps even more importantly, from the plant extracting the water, is that just right condition of oxygen and water creates a subaquatic environment that allows the microbial community to thrive as well. Because remember, plants and the soil microbes are really almost one organism. So this just right condition is really super important for us. So how do we determine what that balance is? Well, there are four aspects to that. The first is we have to consider the climate that we're in. The second is we have to figure out what plants are actually in the landscape. What kind of soil do we have, and that's type, and then also what are the properties or structure of that soil? How is it behaving? Is it a brick or a sponge? And then also, what kind of irrigation equipment are we using in order to deliver that supplemental water? So these are the four things that we're going to explore in the rest of the workshop. So climate is really all the things that determine the weather conditions that actually are affecting your plant at any given time. And the two most important weather conditions are solar radiation and temperature. Solar radiation is actually the most important, and if you only could remember one, it's that one. So in other words, how much sunshine is a place getting? And also, how long are the days? These are two, really important. This is a really important aspect of the weather condition determined by a particular climate. So we break climate into really two categories. We talk about what's called macroclimate. Macroclimate is basically, where's your garden located? Is it at a beach? Is it in the desert? Is it near the mountains, or is it on the plains? Um, some other factors that will affect the weather conditions are humidity and wind speed. And of course, these are going to make a big difference in the mountains and plains. But again, not quite as important as solar radiation. Is your landscape in a grassland? Is it a rural landscape, or is it an urban landscape? These are going to have vast differences in the climatic conditions that are affecting your landscape. Are you near a forest or in a forest? Totally different scenario. And then, as I said, the other climatic conditions are affected by sunlight and things like when does the rain come and is there a freeze? So, is it spring, summer, fall, winter? Do you have these seasons? Or do you only have, two of these seasons? All of that is going to be taken into account when you are determining how much water the plants in your landscape are going to require. That's that what we just talked about is macroclimate. And now we're also going to consider microclimate. Microclimate are the conditions that are in your garden and your garden only. These are things like, where is the sun and where is the shade? Are there wet spots in the landscape? Are there places where you have is it a built environment that has a lot of reflected heat? Those are what we call microclimates, and they are also going to affect the amount of water that the plants need in your garden. So once we determine, what your climate is and where you're located and how that's going to affect you, the next thing is what plants are there, because all plants are going to be removing water out of the soil and putting it into the atmosphere at different rates. Trees are going to be totally different from ground covers. And ground covers that are drought tolerant are going to be totally different from ground covers that are not. Perennial plants are going to be different from annual plants, and shrubs are going to be yet again completely different. So the particular plant that you are selecting is going to give us information about how it grows optimally. And again, that optimal growth is what we're looking for in terms of how much water it requires. I think it's important for us to understand that the mechanism that plants are using in order to uh, take water out of the soil is called evapotranspiration. Now, you don't have to remember that. Just think of it as ET. That's the shorthand for it. And if you ever see ET written anywhere, it means evapotranspiration. And evapotranspiration is a measurement in inches of water over a period of time. And it's essentially measuring in a particular place, so in a particular climate, for a particular plant, how quickly is water evaporating from the soil? And then also, how quickly is water being taken out of the soil by the plants and converted into atmospheric water or water vapor by those same plants. And this process of evaporation and transpiration, which is essentially like a plant sweat, really, that is what we are going to call, the removal of water from the soil. This is called the plant water requirement. When we talk about irrigation, the plant water requirement is how much water that plant is taken out of the soil at any given time and putting up into the atmosphere. It's how much water that plant requires to do all of its photosynthesis and everything else. And different plants have different adaptations that they create or have created over, billions of years that make them more or less adapted to their particular place. And these adaptations are often reducing their own plant water requirements. Examples of these adaptations include things like leaf shape, leaves that are, very small or very, very stiff are less likely to have water removed from them. So they hold on to water a lot better than very large leaves that are, kind of floppy. Leaves that have color that are either hairy, or shiny or gray color, these are reflecting heat off of the plant. And so the plant is not needing to take as much water to cool itself down. And then we also have plants that have adaptations like summer deciduousness. In a lot of Mediterranean climates and desert climates, summer deciduous is a adaptation that allows the plant to essentially go to sleep in the summertime when temperatures are the hottest, when the sun is at its highest, and it isn't really actively blooming or growing. It's, conserving its energy during the summertime. And likewise, we have plants that are winter deciduous. They are adapted to, usually this is a cold, but also a light reaction. So because the days are so short, they are actually going to sleep in the winter time. And many times you see plants with winter deciduousness dropping their leaves and becoming bare because they don't need to do photosynthesis in the winter time. So these are all examples of adaptations. There are others, but when you're looking at plants, one of the things that you're going to be looking for is, does this plant have particular adaptations to reduce its plant water requirement? If so, that's a plant that we want to have in our landscape. Another thing to understand about plants is that they cooperate with each other in the landscape. It's a complete myth that plants are just competitive with each other. That is not actually true. They are completely cooperative, really, and they cooperate through building and managing a very, very complex soil microbial community. And they build that soil microbial community through their root systems. So when we have a landscape that has a lot of different kinds of plants with a lot of different root structures and a lot of different leaf structures and a lot of different heights and so forth, we get actually a more complex system, and we get a system where the individual plants are benefiting from the action of the whole community. So the plants in a very dense and very diverse landscape are actually cooperating with each other to manage the water in the landscape. And essentially what this means is the more plants you have, the more densely planted, the less water is going to be required by the entire landscape. So it really changes the way we think about, even though plants are evapotranspiring and taking water out of the soil individually, they begin to work together so that the whole ecosystem will evapotranspire less if it is highly diverse and dense. So plants can't take water out of the soil if there's no water in the soil. And that is what in order to determine how much water is in the soil, we need to look at the type of soil that we have. So the different soil types hold on to water at different amounts. And we like to think of the soil, the water that is in the soil, as a kind of water bank account. It's available for the plants to remove, and every now and again, that bank account needs to be filled up again with water. That's what irrigation and rainfall are about. But one of the things that we need to sort of be aware of is that water is moving through soil and is held by soil at different rates. And so it's important for us to know the type of soil that we have. And in order to determine the type of soil, you use what's called a hand test for soil. Sometimes we do what's called a jar test. And we have those resources online and in the guidebook for you to do. Now, soil type is, as I said, determining how much water is actually in the water bank account at any given time. And it also determines how the water gets into the bank account. So there are three types of soil that are generally talked about: sand, silt, and clay. But the sand and the clay are really kind of opposites. And so I think it's worthwhile for us to talk about the difference between sand and clay so that you can begin to think about, the behavior of your particular soil based on whether you have sand or clay. So sandy soil is very large particles of soil. And because of that, it actually ends up having the pore spaces are larger, and uh, the soil actually acts a lot like a glass of iced coffee. This is how I like to think about it, and it's an easy way, I think, to kind of an analogy for us. So if you think about a glass of iced coffee, those ice cubes are like the big soil particles, right? So there's a lot of space in there for water, for oxygen. The challenge is that those ice cubes can't really hold on to very much water. If you drilled a hole in the bottom of the glass, the iced coffee would just come right out of that glass, leaving the ice cubes behind. It would actually move through the profile of the glass very, very quickly. And if you tried to pour more in, it would go in very, very quickly. Nothing would stop it. And if you put a straw in there and tried to just take out the coffee part without any of the ice, it would be very easy to do. So it would be easy to extract. This is very similar to how sand is working. Water passes through it quickly. It is not held very well in the soil profile. And plants that are in sandy soils are able to extract whatever water is there very, very quickly, depleting that bank account very quickly. Clay soils are completely different. Clay soils are teeny tiny particles. There is a lot of pore space in clay soil, but it's very, very, very small. And in that way, it acts a lot like a blended coffee in comparison to the iced coffee. In a blended coffee, the ice crystals and the coffee are really very tightly bound together. So if you wanted to try to extract just coffee out of that glass, it's quite difficult to do because the coffee is like stuck to the ice crystals. Also, in a clay soil or in our blended coffee example, putting more coffee into this is quite difficult. It goes very slowly going in. If you drilled a hole in the bottom of the glass, it would drip out very slowly. So a lot of the coffee would be held in that glass, and it would be released extremely slowly. And if you put a straw in there and, like, as I said, try to just take out the coffee, really hard to do. So in that way, the blended coffee is like clay holding on to an awful lot of water, very difficult for water to go in. It has to go in slowly. And it's also draining out of an area very, very slowly. So these are great examples, I think, of how you can kind of differentiate between how soil that is sandy behaves versus clay soil. So once you have that soil water bank account, the amount of water that's there in the soil, and you know how quickly the plants are removing that water from the soil, now you can begin to come up with a timing of when the plants are going to get to a point where they can't really get water out of the soil anymore. They're going to need to have more water put into that soil so that, they can continue to evapotranspire. And so when you start to look at plants, you can actually really put them on a continuum of evapotranspiration rates. And you can essentially say that there are some plants, and a great example of the kind of the poster child of, the fast, thirsty, sweaty plant is cool season grass. This is a plant that has very high evapotranspiration rates. It is removing that water as quickly as it can because it's very, very sweaty. It needs to constantly be taking water out of the soil to keep itself cool. It doesn't have a lot of good mechanisms. And if you don't live in an area where you're getting 40 to 50 inches of water during a growing season, from rainfall, you're going to have to do something to apply irrigation in order to keep that plant alive. But the other plants in a system can really be put on a continuum of plants that are maybe a little bit slower in the way they take the water out. Plants that are called moderate water users. And it's too bad that the terms are water users. It's really moderate water cyclers. Um, they are taking water out of the soil at about half the speed that a cool season grass would be. So they don't need as much water to be in the bank account to keep them happy and healthy. And then there are plants that are so well adapted to a place that they've slowed down their evapotranspiration rate so well that they could really thrive on pretty much whatever water is in the soil bank account. They can go months or very, very long periods of time between watering events. And so if they're in a climate where they're not getting water from rainfall during the growing season, they're okay because their adaptations are making them so they just don't need to have that additional water. So when we start to talk about plants as being low water requiring plants or moderate watering requiring plants or very low, what we're really do is we're saying we recognize that a plant like cool season grass, that needs a lot of water. It's taking water out very quickly. But the plants that we're going to be selecting, they have adaptations that are allowing them to take out water a lot more slowly. And we need to be comfortable with the idea that we do not have to water at the same rate that we would for grass. We could even be going months in between watering if we've selected the right plants. Something else in soil that really greatly affects plant root growth and therefore its ability to access the water in the bank account is compaction. Compaction is when the soil particles have been either mechanically or chemically compressed. So the application of fertilizers and herbicides and that kind of stuff will kill soil microbiology, and the soil actually becomes compressed because, believe it or not, it's those little soil microbes that keep the pore spaces open for the oxygen and water. But so when that compression happens and it becomes compacted, the plant cannot get its roots very deep into the soil. And as a result, it has a very, very shallow water bank to draw its water from. The best scenario for a plant is that it is in a nice spongy soil with really good airspace and plenty of water in it, and it can just put its roots down, as deep as it wants. And everywhere that plant has roots, it can access the soil water bank account. And so the longer the roots, the more water that's available to the plant for evapotranspiration. So when you have shorter roots because of compaction, you're ending up having to irrigate more frequently and very shallowly because the roots are right there at the top. They're not nice and deep roots. But when you have soil that is not compacted, it's acting like a sponge, you actually have longer root depths, and therefore there's more water available to the plant, which means you don't have to water as frequently, And when you do water, you can apply more water to the soil at one, in one setting so that the whole root zone is irrigated. This process that we have in the watershed approach of turning dirt into a soil sponge is really probably the most important thing that you can do for holding on to water and for having a landscape that can thrive on minimal irrigation. This soil sponge makes all the difference in the world. It also combats fires. I mean, it does everything. It's the miracle of a climate-ready landscape. So when you have soil that has been turned into a sponge, this is actually maximizing the plant available water that's in the soil, and it directly reduces the amount of irrigation that needs to be applied. The spongy soil is not just holding on to water in dry times, but it's also releasing that water slowly when it's very wet. So spongy soil is what combats floods. Uh, you see floods because the water cannot absorb into the landscape and be held in the soil. Spongy soil, though, will absorb that water. Spongy soil is actually able to turn compacted soil into beautiful free draining soil and allow those roots to grow super, super deeply. It speeds up infiltration so that when rains come, even if they are heavier rains or, you're getting more volume in a shorter period of time, that's okay because it is infiltrating faster. It's going into the soil profile faster and kind of unintuitively, but miraculously, it's also being held in the root zone for those plants more. Why? Because the spongy soil is actually fostering a microbial growth that fosters root growth. And when you have more roots, more dense roots, more microbes, you have a lot more water being held in the soil for the plants. So spongy soil is the absolute key. The irrigation equipment that you use is also super important to consider because it's going to determine how quickly and also how efficiently the water is being applied to the landscape to fill up the soil profile. So there's spray systems. The best of the spray systems are what are called multi-trajectory rotating nozzles or rotors. These are devices that apply water slowly. They're actually probably 2/3 more slowly than conventional spray heads, old-fashioned spray heads. The droplets of water are heavier, so they stay in the landscape, and they're applying water in gallons per minute. You could also be utilizing a drip irrigation system, and the drip irrigation systems are completely different, of course, from spray. They are putting the water directly at the roots of the plants. The emitters are either applied to a blank tubing or they are already embedded within a tubing at regular intervals, and they're applying that water to the soil directly. It's applied in gallons per hour, and the emitter sizes range from 1/2 gallon to 2 gallons per hour. Gallons per hour. So remember that because it's totally different from gallons per minute, which is what spray is delivering. Now, efficient irrigation is applying that water to the soil, and the trick is we want to keep the water in the root zone. If it goes through the soil too quickly, it will go out of the root zone. And if it spreads out too much, it could actually end up waterlogging the root zone. So we want just the right amount, again, to be in, just in the root zone. Remember, sandy soil is going to need a slower application because the water infiltrates very, very quickly through sand. It's going to flow through very quickly, and it will actually flow out of the root zone and not be available to the plants. It does not, when water is applied to sandy soil, it does not spread out very easily. It goes straight down. And when water is applied to clayey soils, we also need to slow down the application because the water kind of sits and does not infiltrate very quickly, and it spreads out horizontally. So it's challenging to be able to get water to the bottom of the roots in a clayey soil, and it's challenging to keep the water in the root zone in a sandy soil. Both situations are going to require that we're applying the water as slowly as possible. And we are going to want to make sure that the entire irrigation system is super efficient. That means that we are going to look for equipment that has a water sense logo label on it. It's certified, it's well manufactured. We're also going to make sure that the entire system has been designed, installed, and maintained properly. And finally, we're going to try to find weather-based irrigation control so that the timing of the application of the water is based on the things we talked about, the type of plant, the climate, and the type of soil, and not just because, it's Tuesday and so the irrigation goes off. All right, that's how much water plants really need. What are some of the elements of an irrigation system? We're going to start with the water meter. The water meter is the water meter and all the pipes, let's say ahead of the water meter, like a water main and the water service pipes. These are managed by the water service provider, whether it's a municipality or a water agency. But once the water goes through the water meter, it is now officially your water. You're responsible for it, and you're responsible for the main line that gets the water from the water meter to your home. The water meter is essentially like an odometer on a car. It's measuring the amount of water that's going through the pipes of the meter. And there are a couple things I just want to point out because they're critical in all irrigation systems. The first is that there's this little blue leak indicator. This thing is going to be going around even when the flow is very, very low. And if everything is shut off, as we're going to talk about in leak detection, and that thing is still going, you definitely have a leak. You can also find out the diameter of your water pipes by looking on your water meter. It will have a little notation there. This is a 3/4 inch pipe coming out of it. And then the water is being read. Sometimes it's read in gallons, and that's often the case if you have a digital meter. This is an analog meter, which is more common. And the analog meters are actually reading water in what are called cubic feet or 100 cubic feet. Each cubic foot is 7.48 gallons of water. Could they make it more challenging? I don't know. But water is then reported to you on your water bill in 100 cubic feet. So it's reported to you in units of 748 gallons. We have information about how to read a water meter in the packet of information in your guidebook. Now, once it goes through your meter, it's going to go into what's called the main line. The main line is always pressurized. This has got water flowing through it at all times. And this should definitely be what's called Schedule K copper pipe. It needs to be buried 12 to 18 inches below grade. And if you are in a frost zone, it needs to be at least 6 inches below the frost penetration zone. So in some places, this could be, 50, 80 inches below ground. The water coming through those pressurized pipe or the main line is going to need to have a shutoff in order to keep it from flowing into the rest of the house or into the landscape or anywhere else. And so there are a bunch of different shutoff types. The one on the very far left is actually the water main shutoff at the water meter. This you're going to have a wrench to turn. Don't recommend you get out there and do that. It's really only an emergency that you're going to want to have to do that. But as you can see, it doesn't have an easy way to shut off. So you are going to need to use a wrench on it. The other two that you see here are easily shut off. One is called a ball valve. That's the one with the kind of handle. And the other one's called the gate valve. That's the one that you turn and you often see in uh, hose bibs and so forth. Both of those will isolate water in pipes. One of the things that water service providers are concerned about is if water flows through the meter and it comes through the main line onto your property and it goes out into your property or it goes into your house and goes into your sink and so forth. If there is a pressure change in the whole system, it is possible that that water that's already essentially been used by you or been out in your landscape could be sucked back into the main water supply through the meter. And so you need to have some form of backflow prevention on your property. That backflow prevention is keeping the water from being able to be sucked back into the main water system. It protects the main water supply. There are a bunch of different kinds of backflow prevention. The most elaborate is the one in the upper left, which you really only find if you have a swimming pool or a large water feature, maybe multiple units on a property, or a very large property. That's where you're going to see this reduced pressure vacuum breaker. What is much more typical for a residential property is the lower left, the pressure vacuum breaker. Again, it's acting as a backflow prevention device. In some cases, there isn't a backflow prevention device, and so the municipality or water provider is going to be really concerned about making sure you have backflow prevention for anything in your irrigation system. And the way we do that is through something called an anti-siphon valve. These anti-siphon valves are essentially designed to sit high enough above the landscape so that it's impossible for water to flow back into the water supply once it's gone through these valves. You have to use anti-siphon valves if you have no other form of backflow prevention. There are two kinds. One is a spray valve. This does not have a filter on it, and it doesn't have pressure regulation on it. And the other one is a drip valve. This is going to be a low flow valve. It has a filter on it, and it has pressure regulation on it. Both of them, as I said, are sitting above the landscape. They really have to be 6 inches above the highest point in the irrigation zone that they control. So that means if you have a planter that sits higher than where these irrigation valves are, you are not successfully backflow preventing unless the anti-siphon valve is taller than the planter. If you have emitters that are up on a hillside and your anti-siphon valves are down at your house on a lower grade, they are not doing their job. They have to be somewhere that they are higher than that highest emitter, 6 inches above it. Sorry. Also, pressure regulation is a part of an irrigation system. You might have a master pressure regulator because think about it, that water that's coming through the water meter is super high pressure usually, and in some cases it's ridiculously high pressure. It's coming from the water main that's supplying the whole community. So pressure regulation is how you keep the pipes in your house from clanking. And it's also how you make sure that your irrigation equipment is going to operate at its most efficient level. So you might have a master pressure regulator, or each individual valve may have pressure regulation on it. You also might have what are called globe valves. These are valves that are actually installed in boxes and they are below grade. If you have one of those backflow prevention devices that we showed earlier, sort of master backflow prevention, you could have a globe valve installed in a box. And take a look at these pictures, because if you have these and they don't have pea gravel at the bottom and they're not nice and tidy like this, you should really have them redone. This is you need to have access to them. You need to be able to work on them. There are a lot of leaks that can happen at irrigation valves. And so you want to be able to access them. Remember, the irrigation valve is at the end of this pressurized main line. It is essentially holding back water from going into your landscape under pressure. So there's a lot that can happen with those. PVC is actually used both to create the valve manifold, which is what the irrigation valves are, and also the lateral lines that distribute the water out into the landscape, into your drip irrigation or into your spray irrigation. There are two different types of PVC you're going to see in your landscape. Schedule 40, the white one, is really only appropriate for being buried. It's buried at least 6 inches below grade, and the reason is it degrades in sunlight. So if it's exposed to the sun, it's going to get hairline cracks, it's going to break. It is going to be underground, and it's only pressurized when the valve opens up and allows water to flow out into your landscape. So it's only pressurized when the zone is running. The other kind of PVC, Schedule 80, is what you're going to see the manifold made out of. So anything that's above grade should be this gray pipe, the Schedule 80. It's a thicker diameter wall. It doesn't degrade in sunlight, so it doesn't crack. And it is also able to really handle this constant pressure that is going to be coming into your valve, right? If the irrigation main is at the high pressure and it's coming into your valve, that high pressure is going to be stopped by the valve. This Schedule 80 is going to be under pressure most of the time, or all the time, really, coming in, and then some of the time going out of the valve. Your irrigation timer or controller is super important. It's the brains of the operation. It tells you when the irrigation goes on and off, and it needs a dedicated outlet, in some cases, a Wi-Fi connection, and it's connected by electrical low voltage wires to the irrigation valves to turn them on and off. So what could possibly go wrong with something like this? Well, let's look for some clues. Hey, it's 5 a.m. What do you think is happening here? Well, it could be a mainline break. Remember, a mainline break, just the width of a dime, could be losing anywhere from 5 to 6,000 gallons a month. It's a lot. Anywhere that galvanized pipe, it might be connected to copper pipe or to PVC. This is a place where there could be an issue. And sometimes the signs of leaks are not very dramatic. This probably has gone on for a long time here, this leak. Sometimes it's completely invisible. All you see is a mucky landscape. Is there a geyser, a puddle, something? If that's the case, it's probably a broken PVC lateral line or possibly a broken spray head. It could be a broken drip line as well, or a drip line that an animal has bitten into, or that a gardener has, and that could be you, has, hit it with a shovel. Accidentally, of course, but because they're buried, you don't see these lines, and the only result is this muckiness in the landscape. This is a very sad picture because we know at the top of the screen that what's going on there is called low head drainage. That can be fixed really easily by replacing the spray head, but we can't figure out exactly what's happening there in the middle of the picture. It's probably something under the concrete that is broken. And so the question that you need to ask yourself is, when the irrigation was installed and before the driveway was poured, did somebody put down a sleeve or did they cut that corner? Anytime you go under concrete walkways, sidewalks, driveways, anything, make sure you have at least 2 inches, but preferably a 4-inch sleeve that you can run your irrigation pipes through. You can run your irrigation wiring and even your landscape lighting wiring through. And it makes it really easy to replace the pipes if there is something going wrong. Now, those are things that we see happening, breaks and so forth, but There's also this inefficiency happening because of the way we apply the water. As much as 50% of all the water that we're using outdoors actually runs off a landscape. It doesn't make it to the landscape to begin with. And here's a great example. I mentioned it before, this low head drainage. This is when you have a even slight slope. If the spray head doesn't have a check valve in it, when the irrigation controller turns off, the water that is in the lateral lines all flows down to the lowest head. And that particular sprinkler head thinks that the pressure is on again. And so it pops up and it lets the water out. And so all the water that was in the pipes that could have been used the next time for irrigation is actually going to drain out and just run onto the sidewalk or whatever. So we need to make sure that our sprinkler bodies have check valves in it. And the good news is if you're getting WaterSense approved equipment, they probably already have the check valve in them. But if you have older equipment, this is something that you're going to want to replace. Hey, if you're seeing misting when spray irrigation is going on, it means the pressure is too high. High water pressure destroys both a spray system and a drip system. You need to install a pressure regulator. It's possible that your pressure is so high that you need multiple pressure regulators, one for the house and one for irrigation. When water is applied, but it's blocked by shrubs or the configuration, the design of it isn't exactly correct, we can find that water isn't actually even being applied to the landscape. It's just being applied to the adjacent hardscape. This is called overspray. And when you get enough overspray that it starts to move, it's called runoff. You might have spray heads that need to be adjusted because this is keeping water from going onto the landscape. Tilted heads are a perfect example of that. And the thing that you see on the right is a low pressure head. When you see a spray head operating like that, it means that there's either a break in the line or the pressure now is too low and it hasn't enabled that spray head to pop up. In most cases, it means that there's a break in the line. Okay, that's what can go wrong. Now, how do we track all this down and figure out where things are? Well, I want you to take leak detection very, very seriously because your landscape can easily be overwatered as a result of leaks. There are as much as 1 trillion gallons of water wasted each year, which is enough water for 11 million homes in the US. So it's a really serious thing. And, the easiest way to do it is to connect with a professional who can come out and use an acoustic sensing to locate the leaks, but you can do it yourself as well. Your irrigation system is not that difficult. Go for it on a Saturday morning. We're going to monitor this irrigation system by looking at this little indicator on the meter. Remember, I told you that if that thing is moving and everything is shut off, you have a leak. So by watching this little indicator, we can determine where the leak is located. So the first thing is we make sure that the irrigation controller is off so that that's not inadvertently going on. And we walk around and we listen to the irrigation system. We listen for the sound of water dripping or even running. And what we're going to do is we're going to actually start at the water main and we're going to move out into the landscape, going systematically through each area, shutting things off and observing to see what's going on. The main line, of course, is that major leak I told you about, the 6,000 gallons a month potential. Main lines are often installed with the wrong type of copper pipe and they do crack. So please be aware. This is one of the most important places for you to start. You shut off the irrigation, you shut off the water to the house and the landscape, wait for 10 minutes. And if that meter is running, that little dial, you probably have a main line break because there's no water going into the house or the landscape. This is a setup that you can see here. There's one valve that controls the house and one valve that controls the irrigation. This gate valve that's here in the very front is a hose bib shutoff. So all of these things need to be closed. And when they're closed, if there's water running through the meter, it means it's mainline. If it's not, if the leak is not happening with the main line, then you want to try to figure out, is it in the house or is it in the landscape? And so first you shut off the landscape water and you wait to see if there's any leak happening in the house, and if it isn't, there's no leak in the house, and then you do the opposite, which is turn off the water to the house and see if it's in the landscape. So it's just really a systematic going through. But look at all the potential things that could be leaking. Backflow prevention and pressure regulators definitely can leak. Hose connections. The shutoff valves themselves might be damaged, or there might be debris on the inside of them. And of course, if you have an irrigation manifold like this one that used Schedule 40 pipe instead of Schedule 80, you're pretty much guaranteed to have some kind of hairline cracking from temperature differentials. This is just a can of worms. This needs to be replaced. So once you have kind of determined, all right, the leak is not in the house, it's out in the landscape. Now you're going to have to turn on each of those valves. And the easiest way to turn on each of the valves and isolate each irrigation zone is to go back to your controller and turn it on from there. If your valve itself is leaking, it probably means it has debris in it. It's a very simple fix. I know it looks really intimidating, but you can actually take that top off and clean out the inside, and that will probably fix the leaking valve. All of the points of connection, whether they are spray or drip, are going to be places where there could be debris and so forth. And so it's perfectly reasonable to unscrew spray heads and unscrew drip lines. Check and clean your nozzles. If you have spray, very easy to just take them apart, clean them off, and then put them back together. If you've got pooling water in the landscape, it could be from a lateral line that was either broken just from old age, or it may not have actually been installed properly. If you're having your irrigation done, make sure that you are observing how, for a little while anyway, make sure you see how the pipes are being glued together. I've seen lines that aren't even glued. So that's not good. And especially if you're converting to drip irrigation, you want to make sure that these lateral lines are really well glued together, because now there's going to be a lot of pressure differential in those lines. So we want to make sure all that's happening. We've got a YouTube video for you to look at to see how to do that. Now, let's convert our spray irrigation to drip. Why do it? Well, lots of reasons. I mean, if you've got ground cover and you've got a big open space, spray is probably the way to go. I'll be honest, drip irrigation has a lot of potential issues with it in these very large applications. So if you're trying to deliver water, uniformly over a large area, the best way is to stick with highly efficient spray. But if you're looking at planter beds, trees, smaller areas, the way to go is with drip irrigation. Drip irrigation is delivering water in gallons per hour. Don't forget that. If your drip irrigation ends up running for 15 minutes, it isn't delivering enough water. It needs to be running for 30, 40, an hour at a time. Whereas if your spray emitters are on for 30, 40 an hour at a time, that's applying a lot of water to your landscape. Again, we talked about the fact that the drip irrigation is delivering water directly at the roots, which is great. It also reduces the incidence of unwanted plants. So weeds and so forth are less likely in a drip irrigated landscape. And your runoff is usually slower, although it is possible to design a drip irrigation system incorrectly and have the applied water be too high for the landscape. When you have an irrigation valve that is running a drip line, it needs to look like this. It has a filter on it and it has pressure regulation. Both are important. That filter needs to be cleaned out twice a year. You can see here, this filter hadn't been cleaned out in a really, really long time. It's very, very simple. It doesn't get replaced. It just gets taken out of the filter holder and rinsed off and put back in. That's it. Super simple. But that filtration is how you keep gunk from gumming up your emitters. Simple as that. When you lay out drip line, you are thinking about where is the main point of connection. In other words, where does my flexible tubing connect to my PVC lateral line? And the PVC lateral line is, you want to place these points of connection around your landscape if you are doing a new one. If you are converting an old spray system into drip, you will probably be abandoning all of the spray heads that are in the landscape and going back to the very first spray head that is the closest to your irrigation valve and converting that particular spray head into a drip connection, a point of connection. You're going to lay out the tubing in the landscape either in a grid or random pattern, and at the end of the line, you're going to install what's called a flush valve and a tattletale. I'll show you what they are. First, the point of connection. This is where the lateral line meets the tubing, and there's a riser that comes up from the lateral line, and it connects into the tubing. There are assembly pieces that convert this. The irrigation is going to be either inline drip or point source. Inline drip is tubing that has emitters already embedded in the line at regular intervals. It could be 12 inches, 18, or 24 inches apart. This is a really good structure or really good equipment if you are going to be doing like a grid system. You could also use what's called point source or online drip irrigation. This is where you have a blank tube that goes through the landscape. No water is going to come out of it except where you have actually put an emitter into that blank tubing. This is good for plants that are spaced apart, spaced more further apart. And it really allows you to control the amount of water going to that particular place, that particular plant. Just forget about 1/4 inch tubing. This is not an appropriate type of irrigation system for a landscape. It's great if you're going to do a vegetable garden, a planter bed, a little planter or a container garden. Okay, yes, wonderful. But for a landscape, this is just too many points of connection that can actually break, and it's highly inefficient. When you are laying out your 1/2 inch tubing, you're going to either do it in this inline grid pattern, as you see on the left, which is essentially rows of tubing. And this is inline, so it has the emitters already embedded there. This would be appropriate if this was like, all ground cover, for example. That's a great use of that. Alternatively, you may want to do a random pattern. So you've got plants that are spaced further apart. This, you don't need to have water, every 12 inches. So you do the blank tubing and then you install the point source online emitters into that blank tubing as you snake the tubing around the plants in the landscape, as you see on the right. If you're doing a drip, you're going to want to make sure that you are spacing the grid lines far enough apart and that you are aware of the spacing of the emitters so that the emitters are basically creating like a triangle of water application so that you're getting a uniform water application. The emitter flow rate that you want to use for a sandy soil is really at least a gallon per hour. If you have clay soil, you want to use the lowest flow rate. So this is going to be 1/2 a gallon per hour. And typically your emitter spacing is going to be 12 or 18 inches apart. And then the line spacing, so the space between the individual lines is going to be 12 inches apart for sandy soil, 18 inches apart for clay soils. And this offsetting of the emitters is really kind of important so that you're getting enough water coverage. Trees are a special situation. You want to make sure that you have concentric rings of irrigation going around them, spaced anywhere from 12 to 24 or 36 if it's a very big tree, inches apart. And the objective here is that you have enough circles around the tree to create a uniform watering of 50% of the soil. So 50% of the soil surface needs to be wet when you turn the irrigation on. Then you know that you're getting enough coverage under this tree. Stay away from the trunk. No emitters against the trunk, please. That is a sure way to kill your plant. When you are laying out a random pattern, in particular, you're working on a slope, you want to make sure that the emitters are actually placed on the uphill of the plant. See how the plants are here and the tubing is on the uphill side. This is because water flows down. And so if your emitter is underneath the plant, it's not going to the plant. How many emitters per plant? Well, it really depends, but a great fail-safe is to think about getting at least a gallon per hour on each plant. And so that is usually 2 emitters for the smallest of plants at half a gallon an hour, or 2 emitters at 1 gallon per hour for larger plants. It of course depends on the slope and everything, but the most important thing about your emitter placement is that it is on the root ball. It's not outside of the root ball. Let me show you an example of that. So when you have the tubing and you've placed the emitter into it, the pointy end goes into the emitter, goes into the tubing. You want to make sure of a couple things. First of all, you want the emitter to be parallel to the ground, not sticking straight up, because when it sticks straight up, that's how it gets clogged. You want it parallel to the ground, pointing toward the plant. And you want the tubing itself to be touching the ground. Then again, the actual placement of the emitter is halfway between the trunk and the edge of the root ball. And don't forget that the root ball of the plant, especially if you're planting new plants, may be a lot smaller than that nursery container that you got. So you really want to have it be on the root ball. So if your plants are suffering, like this one clearly is, you want to check first your emitter placement. So here's the emitter in the landscape. Oh, it's pointing straight up. Yep, that's not right. But let's ignore that for a second. Where should it go? It should go on the root ball. If that emitter were on the root ball, this plant would not struggle. And there are lots of repair kits that you can use for drip. There's a goof plug in case you put an emitter in the wrong place. There are drip repair couplings that allow you to cut the drip irrigation and compression fit it back together. So all of that is pretty easy to repair in drip. Now, at the end of the irrigation line, you're going to want to have 2 things. One is a tattletale, which is going to pop up and tell you if something is wrong, like if the pressure isn't high enough, it won't pop up, but it'll tell you that either that something is wrong, or it'll tell you, hey, this irrigation zone is on. Remember, the drip is buried, so you don't know that unless you actually see the tattletale. The other thing that you're going to want to have at the end of the line is a flush valve. Flush valves are how you keep gunk out of your irrigation system. And it's good to put these 2 close to each other because eventually stuff grows up and you can't see where the flush valves are. U-shaped staples should be used for putting down the irrigation tubing, not flat top staples. Those are for fabric, which you're not going to use anyway. You want to use the U-shaped staples. And flush valves are really something that contractors love to install. They love to install those automatic flush valves on the left, which essentially shoot water out into the landscape every single time the irrigation zone goes on. Forget about that. It's a waste of water. You just want to have a flush valve that you can open up easily and you can allow water to go through the whole line and flush out all those emitters and any gunk that's in there. So look for a manual flush valve, either a figure 8 like you have at the top, or manual, actual valve at the bottom. And then you put that flush valve pointed into the landscape, not at the very edge, of the sidewalk, because you don't want the water to run off. You want it to run into your landscape. Putting it into a box is a great way to do it. They're not that difficult to install in there, and that way, again, you can see it, you can keep it clean, and it all works. Make sure that you cover your drip tubing with 3 inches of mulch at a minimum, 4 inches if you can do it. Okay, finally, how do we water more efficiently? Well, look, we talked about the fact that plants need water, that's evapotranspiration, and the curve is peaking in the summertime. That's when days are the longest, temperatures are at the highest, and so the plants are going to demand water out of the soil, at a higher rate during this growing season, which is really from May to September, pretty much everywhere. And again, that's determined mostly by the length of the day. So you can see that this evapotranspiration curve, it's really low in the wintertime, and then it peaks in the summertime. June, July, August usually are the highest evapotranspiration months. When you plot the evapotranspiration curve against your rainfall curve, this is going to tell you how much water you're going to have to apply in order to keep your plants happy. So the difference between the evapotranspiration or the water requirement and the rainfall that it's getting is going to have to be made up with irrigation. In temperate climates that get summer rain, this is what that looks like. It's possible that outside of the two black lines, which are really indicating the growing season, that you can be a lot more judicious with the application of water because the days are getting shorter. But for sure, in the middle of the growing season, there's going to be water needed. And if you live in a Mediterranean climate where all the rain is coming in the wintertime, your evapotranspiration demand is going to be even higher in the middle of the summer. So there are a lot of strategies that we talked about in this class already about how you reduce your irrigation requirement. One of the things that you're going to want to do is get yourself a soil probe so you can see what's really going on in the ground. Also, getting a dedicated irrigation mainline and meter is a great way to be able to see very clearly how much water is going into the landscape so that you can program your controller. If you have a new garden that you're building, think about hydrozoning. Hydrozoning is essentially breaking the landscape up so that the different plant material and irrigation zones are corresponding with those microclimates that we talked about in the very beginning. Sunny areas are together, shady areas are together. Plants that are requiring more water, like grass, that's separate from plants that require less water, like native plants. If you have an existing garden, convert your planter beds to drip. And every single time you have a separate hydrozone or an area that is either watering a particular planter bed with plants of a particular water requirement, or a different type of irrigation, spray or drip, or you have plants that have different root depths, trees versus ground covers. Break those all into different hydrozones. Add an irrigation valve for each of those hydrozones. Irrigation valves are, in the long run, very inexpensive control of your irrigation. The more irrigation valves you have, the more you can control the water going into your landscape. It's a great investment. Make sure that every hydrozone has its own irrigation valve. And at the very least, remember that if you are trying to irrigate for that evapotranspiration curve in the growing season of the summer, you don't need to keep that same schedule in the fall and in the spring. In fact, it really is detrimental to your garden to keep a fixed schedule like that. Dial it back in the fall, dial it back in the spring, turn it off in the winter. If you're in a climate that gets cold, of course, you're going to winterize in the fall and it will be off until the late spring. If you're in a place like a Mediterranean climate where you're starting to get your uh, winter rains, then you want your irrigation to be off anyway so that you can maximize your rainfall. Installing a smart irrigation controller is also a really great investment. These are irrigation controllers that are looking at the weather in order to change the runtime or the days that the water is actually being applied. And it saves a huge amount of water over manual controllers. And it can track your water use so that you can actually make schedules. And consider hand watering sections of the garden because it's totally legitimate. I mean, heck, I really love oscillating sprinklers, but that's another story. We can actually grow these beautiful and climate ready landscapes if we use the right amount of water and not overwater and not underwater.